Okay, welcome back once again. So we will continue homogeneous nucleation. In previous video, we have derived the expression for R dash, that is a critical nucleus, 2 gamma divided by delta GV, and excess free energy delta G dash is equals to 16 pi by 3 gamma cube divided by delta GV whole square. These are the two important expressions. These are the two expressions that we derived in the last video lecture. In this video lecture, we are covering expression for nucleation rate, and nucleation rate for both homogeneous as well as heterogeneous nucleation. Okay, so as we seen in the previous video lecture, this is the graph that we got from the volume free energy and the surface free energy overall. That is, below, if the radius of the nucleus is less than the critical radius, then this is called as a cluster. If the radius of the nucleus is greater than the critical radius, then this is called as a nucleus, stable nucleus. So this is we have learned in the previous video lecture. Now first we will learn, so what is the average number of the clusters that is formed in the liquid. This above the, if a temperature is greater than Tm, then this expression is valid for all the values of R. Wait a minute, I will write clearly. This expression 1. Expression 1 is valid if T is greater than Tm for all values of R. Okay, this is the first thing, because the clusters present in the liquid, this is the liquid state, above Tm, all the whole system is in a liquid state. The clusters present inside, the number of the clusters can be calculated with the help of this expression. If we consider temperature below Tm, the cluster size I will take a new screen itself, so that this is n equal to n naught exponential of delta G R divided by kT. Okay, if the temperature is less than Tm, then cluster size R should be less than critical radius of nucleation, according to this graph, right? Then only this equation, above equation is valid. Okay, So T greater than Tm for all values of R above equation is valid. Okay, so here N naught is actually I should tell before the starting itself. N naught is the total number of atoms in the system, total number of atom in a system, and delta GR, this is R, excess free energy associated with the cluster, excess energy associated with clusters. Okay, then K is Boltzmann constant. Here, this is the expression for number of the clusters that is formed. Yeah, this graph indicates the increase in the size of the clusters with respect to the undercooling. As we increases the temperature, decreases the temperature, that is increases the undercooling, the size of the cluster goes on increases. Okay, the when it reaches to the this point, that is delta T Tn, it's no longer, clusters are no longer part of the liquid, it's a part of the solid. After this undercooling, the clusters are converted into the stable nucleus. This is a R maximum. R maximum is the maximum size of the clusters. Okay, now we saw the size of the clusters with respect to the undercooling. Now, now this size of the stable nucleus with respect to the undercooling. As we see, there is a critical radius is inversely proportional to the undercooling. That is the delta T undercooling. As we increase the undercooling, size of the critical nucleus will decreases. This can be seen from this graph. There is R star is goes on decreases with increasing in the delta T. Above this one here in this area, size of the critical radius is so large that it's a virtually its formation of the nucleus is very difficult with a small undercooling. Because of this one, we require a minimum amount of the undercooling to nucleate any new phases in a given solid. That's why after this this undercooling, a stable nucleus will form. From here, as we increases the undercooling, that means decreases the temperature, the size of the critical radius will goes on decreases. Okay, so this is the importance of this graph. Overall, this graph will shows so what is the minimum undercooling required to start the nucleation or to convert from clusters to stable nucleus. Now we are jumping into the rate of homogeneous nucleation. This is a homogeneous nucleation rate. Previous slide we saw the cluster nucleation of the clusters. Now we are shifting to this part. In previous slide we have seen this part and we are now jumping into the this part of this part. This is the nucleation rate. In a liquid, initially we have C star amount of clusters that's present, number of the clusters present in the liquid. This is from the previous expression only. This is clusters plus metric cube. This is a C naught is a atoms per unit volume. C naught is atom per unit volume. Okay, then we can write rate of homogeneous nucleation is equals to F naught into C naught exponential of minus delta G star homogeneous divided by KT nuclei per metric cube per second. Here F naught means the complex function. Complex function and delta G star homogeneous is a free energy associated with the homogeneous nucleus. Okay, then we can write this expression in terms of the undercooling, that is delta G star, as we know that 16 pi by 3 surface free energy whole cube divided by delta GV whole square. This expression can be substituted here and we can get the relationship between the homogeneous nucleation, rate of homogeneous nucleation with respect to the undercooling. Then we can write it as homo equal to f naught c naught exponential of minus a divided by delta t whole square. Okay, this a can be written as 16 pi by 3 gamma cube tm square lv square and kt. The rate of homogeneous nucleation is exponentially related to the square of the undercooling. Square of the undercooling, and we can plot this graph. This graph, there is a rate of homogenization with respect to the delta T. With a small narrow range of temperature, there is an explosion of a nucleus will takes place. This is because of this previous graph. Until this cluster size reaches to this particular undercooling, the it's a clusters is a part of the liquid. When it reaches to this undercooling, this delta Tn, they are not at all part of the liquid and they are converted into the solid. Hence, there is an explosion of a nucleus will takes place. With a small narrow range of temperature, the rate of nucleations, homogeneous nucleation will increase rapidly. Hence, it is shown in a straight graph. Okay. In practical solidification, homogeneous nucleation is rarely encountered. Instead, we are seeing in normal day-to-day life, the solidification is heterogeneous type of nucleation will take place. Because the nucleations, so what's the main reason that we will see only the heterogeneous nucleation? We will come to know in the next video. Okay, thank you.